Swayam Prabha. Digital India. Educated India.
Few classes I might have given the impression that it's a mathematics course. It is not. It is definitely a chemistry course, symmetry course. So let us do a little bit of that, okay, and then we'll come back. But before anything, I'd like to go through the mid-sem questions. The first question, I have not corrected the answer sheets yet, but the first question has convinced me that we need more practice in this point group business. So I am going to give you one more assignment on point groups. Please work them out, and then one day beyond these regular class days, we can have a tutorial session as Vishnu had suggested, and we can just discuss those answers. But you really need more practice in this. That's what I thought that this is easy, but you need to work out maybe 50-60 more point groups, then you will be masters. Let us discuss what we had. What is the first one? What is this? Tell me. C? D2, right? Where is the C2 axis? This is one C2 axis, and joining these two, is that a C2 axis? What is the C2 axis? So what is the position of the perpendicular C2s? That's what I am asking. The vertical C2 is quite obvious. In between? Through which plane? Perpendicular to the plane of the slide means you are saying joining these two, right? Is that C2? This thing that is looking like an X. If I join the front with the back, is that a C2 axis or not? So what are we joining then? Aren't we joining the midpoints of the bonds? Right? So if you join the midpoints of these bonds, this one and this one, will that also work? No. This one and this one. Will that work? Huh? What are we joining? There is no atom here. This is a midpoint. That's what I am asking. You should join the atoms. If you join the atoms, is that a C2 axis? Sure. What is this molecule called, by the way? Do we know? It's called a twistane. So you can see the twist, right? It's full of twists. Yes, it's a twistane. All right. So these are the two C2 axes. Any other symmetry operation, symmetry element? No. Right. Okay. So how many marks are there for this? 2.5, right? So the way we are going to grade is, if you identify all the symmetry elements correctly and do not write anything extra and get the point group correct, then you get 2.5. If you write the correct symmetry elements and get the point group correct, but are innovative enough to identify more symmetry elements that other mortals cannot see, then you get 2. Okay? And if you don't get the symmetry point group correct, but I have got at least some correct symmetry operations, no matter whether you get extra symmetry operations or not, then you get 1. So it's very difficult to get 0 out of 2.5. Okay? Right. Second one. It is D3H. Is the second one D3H? Do you see the C3 axis? Where is the C3 axis? Joining the two irons. Is that C3? Check. CO, CO, CO. Then this is CO, CO, CO. Then again in the middle you have CO, CO, CO. C3 axis. Alright? Don't believe me? Okay. Do we have perpendicular C2 axis? Where are they? Passing through? Two carbons, I'll join two carbons, then I'll get a C2, is that right? Then? So I can draw infinite number of lines through bridging carbons. Isn't it better to say joining the O and the C? So it's along the CO bond, isn't it? Along the bridging CO bond. That is a very specific way of saying it, isn't it? Along the CO bonds, along the bridging CO bonds. So there are three such. So those are the C2 axes. Alright, Anup? You see C2? Very good. Plane of symmetry? All planes will be like that. Which one? Where is the plane of symmetry? Now define the plane. 3 points make up a plane. The three bridging carbons, or if you want to make it more interesting, the three bridging oxygens, three oxygens in the bridging carbonyl groups, or whatever you want to say, the three CO bonds. That is sigma. Is there any other sigma? Where are those sigmas? They are sigma Ds, right? Where are those sigma Ds? But do they matter in the nomenclature? They don't, right? So you have C3 principal axis, you have three perpendicular C2 axes, and you have a horizontal plane. It is D3H. So if you have written all this and nothing else, you get 2.5. If you have written all this and you have also discovered some more C2 axes or some more sigmas and all, you get 2. In fact, if you have not written sigma D, I will give you 2.5 if you have got D3H correct. That is what you wanted, right? No. You have written what? Sigma D. That's not a problem. It's correct, right? So why will you be penalized for that? But if you have, even if you have missed sigma D, I don't mind, because after all, finding symmetry point group was the question. Okay, what about this? This one. What is the name? Does anybody know the name? I don't. But which symmetry point group is it? Looking at it first glance, I thought it is C4 because it has a square. Is there a C4 axis? No. Why not? Because after all, this chlorine goes to chlorine, this chlorine goes to that chlorine goes to this chlorine. So why is this not a C4 axis? The problem is with hydrogen and methyl groups. So if this is not a C4 axis, what can it be? Is it a C2 axis? See, this CCH3 is above the plane. This CCH3 is below the plane. So if you take the axis that is perpendicular to this square, then it does not give you a C2, sorry, what is that? That's a C4 operation. So you turn it around, CH3 goes to CH3, fine. This CH3 goes to this CH3, that also is fine. What about this H? This H is above the plane, this H is also above the plane. That's okay. This is below the plane, that is below the plane, that is fine. And what else? This CH3, oh, okay, fine. So which axis is it? Looks like it's a C2 axis. Right. Is there any other axis or plane or anything? Do you have put two perpendicular C2s? Where? Midpoints of the opposite bonds. Let us see. You are saying there are going to be C2s, right? Are they C2s? Huh? Are they C2s? They are not C2s. They are not C2s. They would have been C2 if the chlorine was here and if it was on the plane. Understand? So this is not a C2. Understand what happens if I perform a C2 about this? I just draw this. What you are saying is, you are saying this is a C2. Now you perform the C2 operation, it is not a symmetry operation. Right? Which lecture is this? I have now lost track. Is it 11 or 10? Is it 12? 12. Alright, we agree that that is not a symmetry operation? That is not the symmetry operation, then the other one will also not be a symmetry operation. So what do you have? You have C2. Is there any plane? No plane. So you have a C2. So which point group is it? Okay. It's a C2 as well as an S4. And if you remember the algorithm, we had said that the algorithm comes handy only when you have nothing other than a Cn axis, which also doubles as is S2n axis. Then the point group is not Cn, it is S2n. Right? So which axis, which point group is it? S4. Now this one. I put white ink on this 1, 1 dash, 2, 2 dash. Is this big enough? You can see? Can you see? Now tell me what is there. Yeah. I took so much of trouble making it big, it became small again. Anyway, where is the C2 axis? Through calcium, of course, and bisecting the O bond and bisecting the C double bond C bond also. Okay, bisecting the O line. All right. And now I think you can see it better because you see this, what is this? This thing has developed a mind of its own. Okay. So see, this is 1 dashed, huh? This is 2, this is 2 dashed. The problem is this is also 1 and that is 1 dashed. Unfortunately, that should have been 3, 3 dashed. That would have been easier. So you understand, right? 2 and 2 dash will exchange place. This one, equatorial 1 and equatorial 1 dash will exchange places when you apply C2. Is there anything else? Any other symmetry operations, any other symmetry element? Sigma H is not there. What about sigma V? This ONNO containing calcium, the equatorial plane, is that a sigma plane? Is that a plane of symmetry? No, right? Because this bridge is from this nitrogen, this bridge is from this nitrogen. It is not a sigma plane. Is there, so what have we found? We found a C2 axis. Is there an S axis? S4 axis? No. So it is C2. Okay. So complicated molecules were simple point groups. All right. And you cannot imagine what kind of badgering I faced while photocopying the question papers. A colleague from organic chemistry came and said, "What is this? Why are you teaching organic chemistry?" Another colleague from inorganic chemistry says, "Why are you dealing with our molecules?" Now, what is, all molecules are physical molecules, there is no unphysical molecule. This was easy. Work out the group multiplication table using the symmetry operations of D2 point group operating on unit vectors along 3 Cartesian coordinates. That was easy, I hope, right? I don't need to go through this, you can work this out. I actually broke up this question into 3 parts or 4 parts. Second part was the subgroups. Identify the subgroups present. How will you identify subgroups? How many subgroups are there? What are the subgroups? So you have to have distinct groups among the groups. There should be nothing outside that subgroup in the collection that you take. Okay, they have to be interrelated among each other. Okay. Now that was the typo that I corrected here, D2. Now work out the 2 possible group multiplication tables for a general group of the same order as D2 point group. What is the order of D2 point group? 4. And this is something we have done in class, right? So when you have 2 subgroups, one is a cyclic and the other is not, isn't it, for H equal to 4. So that is all that you had to do, and then homomorphism means exactly the same multiplication table. So you have to compare this with that and do it. So this is perhaps the easiest question. What was the next one? So here, for n-dimensional functional space, justify OR Fk equal to this. Many people have written many things. All I wanted was, I wanted you to tell me that this djkr is the transformation matrix operating on coordinates, and the reason why I am using djk and not dkj is that when I write OR, we are working with orthonormal functions. If you wrote that, then I am happy. If you wrote something else that also makes sense, then also I am happy. Makes sense in this context, of course. Then we had, this was the toughest question, but there is a reason why I wanted to ask this. And whoever has attempted this has actually made a smart choice. I think everybody has understood what I wanted from this. We had written down this recipe in the class before last or in the last class. I wanted, class before last. So I wanted you to take these matrices, put the values in the recipe and go as far as you could. Actually, you can go all the way. Who went all the way? Anup, did you go? It is just that you get ugly numbers. You are getting 0.44 square root of something and something like that. But then one thing to remember, in case you go wrong in the middle, was that we are dealing with a Hermitian matrix. So you could never get an imaginary number. If you got an imaginary number, that means you went wrong somewhere. So whoever could go up to that and wrote, and whoever has written after that this is how I should proceed afterwards, you get full mark, no issue. Okay. Now the reason why I wanted to ask you this question, after all, your examination does not, that is also a learning process. So what I wanted you to understand is 2 things. First of all, we can actually plug in numbers and work this thing out, point number 1. Point number 2 is that it is not necessary that you will always get very simple, nice numbers. You do get ugly numbers if you have to do things numerically. That is why we don't want to do things numerically, right? That is why we want still to develop the theory further, so that it will reach a situation where we will not get ugly numbers anymore. See, now that we are working with character tables, you will see that things are very simplified. Today we will encounter a situation where it is not all that simple with character tables. But even that is better than those square roots and all that you are getting, right? So this is the difference between doing something numerically and doing something theoretically. Many of you are going to do simulations. So what you don't realize is that the computer does for you what you try to do in the mid-sem exam there. The computer crunches all kinds of ugly numbers that you don't like. Okay? If you want to do it numerically, you will have to deal with these ugly numbers. Okay, fine. Now that was 3. 4a, what happened? There is no 4a? What am I doing? This is where I am a little disappointed that some people had so much of difficulty, because the point is I have told you what are there, and that more or less people wrote correctly. But after that you should have been able to work out the character table. I told you to the practice, right? So we will work out two more character tables today which are much smaller than TD, but which have complex numbers. So I think everybody knows now how to use those 5 rules to work out character tables. Now here there are 6 marks. So even if you have not been able to work out the character table completely, you can get full marks, provided you have shown that you know how to, you know the rules and how to use them, and you write down the headings correctly, and you have gone and you got the Mulliken nomenclature correct. What are the Mulliken nomenclatures for these symmetry species that you got? So here we encounter a 3-dimensional representation, 3-dimensional irreducible representation.
How do you call the keys T1 and T1 and T2? There was some other.
There, if you have got confused, I don't mind, because the thing is, this 1, 2 is very well defined for 1-dimensional representations. For E and T, it's a little more. It's not impossible to figure out. You still look at the characters, but there, if you have written T1 instead of T2, I'm fine.
Is it just differentiation? If you want to differentiate one key from the other?
Yeah, but that also has a basis, like your A1 and A2, but then that is not something that we'll discuss in very great detail. It's a little more complicated. Okay, so I'm fine if you write T2 instead of T1. Okay, but that is also from the characters. Now, 4b, in the context of symmetry and character tables, we prefer to deal with unitary representation, and what I must have said in the class at least 25 times is that one reason for doing that is that they are easy to handle. I wanted to know what are the other two. So you tell me what are the other 2 reasons? Orthonormal, yeah, they deal with orthonormal basis sets. So yes, so it applies to great orthogonality theorem. What else? First of all, it conforms. So both answers stem from orthogonality. First answer I was expecting is this, that then you can use orthogonality theorem. The second answer I was expecting is that, yeah, okay, you can expand a little bit on that. We can always switch bases and go to orthonormal, that is right, but I was actually expecting something else, and that would come if you inspected the character tables a little carefully. What do we have in character tables? What is written on the right hand side? X, Y, Z, Rx, Ry, Rz, right? So on and so forth. So these are all orthonormal, these are all from orthonormal basis. Generally, why is it that we are studying all this? Eventually you will see we are going to work with bases which are orthonormal in nature. Even if we work with orbitals, they are orthonormal, right? So that is the answer I was looking for, the second one. But if you have given a reasonable different answer, you get marks, no issue. Marks are not really the issue. This is the last question, 4C. The representations obtained for C2V point group using the 2 hydrogen atoms as bases are D, dC2, d sigma V, d sigma V dashed. What is the answer? Are they reducible, or are they, I mean, is this a reducible representation, or is this an irreducible representation? Now you tell me what you have written. Has anybody written irreducible? There is no harm in owning up. You have written. So now I want to know your logic. There is a reason why I am asking the question. Why have you written it is irreducible? Actually, I can defend that it is irreducible. It is not, just to make sure that blood pressures don't go up. It is a reducible representation, it is correct. But I could, in a way, argue that it is irreducible from what I have studied so far. You want to say something? So I could say that this is not block factorized, and I have studied that reducible representations must be block factorizable. So that's the point. So it is not block factorized, block factorizable. Yeah?
It should be block factorizable,
Yes.
not block factorizable.
Right. So this is irreducible. It's not. Now you tell me why this is reducible. Sorry. So why does this have to be reducible?
DE and chi is equal to 2. So we get 2 square is equal to 4, which should be the total H of the group. So other chi would be 0, which is impossible. We should have 4 representations. So for the first one, we will have at least one.
Well, the answer I was expecting is that we have worked out C2V character table in this class, right? So the answer I was expecting is that for C2V, we know that you can only have 4 one-dimensional representations. You cannot have a 2-dimensional irreducible representation. Now you are saying the same thing, but as usual, you can think of a more complicated explanation than I can. What was that?
We know that.
What do we know?
And there are 4 one-dimensional.
Oh no, what you can work out? You know that sum over I Li square has to be equal to H. What is saying? So which implies that's how we did it, right? It's not a question of knowing. We have to know those 5 rules. That you cannot go without. You have to know something, right? At the end of the day. So, but what I wanted was application of that. It's fine. What you are saying is also correct. What I had said in class is that if 4 square numbers are equal to the sum of 4 square numbers equal to 4, and if they have to be integers, positive numbers, every L has to be 1. It's not possible to have 2. That would be the logic.